All right. Good morning, everybody. We'll begin in a few. Actually, it's exactly 9:30 now. How's everybody doing? I can now only see three people's faces. Remember, if you can, it'd be nice to have your camera on so that I can like see your reactions. And I just, as I'm saying that, I realize I don't have my camera on. We'll do that. Um, so yeah, it'll be nice to see your reactions. Whether we're going somewhere or I need to explain something again. But welcome to today's lecture. Before we begin, there were a couple of things that I wanted to mention. Um, let's see if I can do this. Yep, there we go. So I did update for some of you who already sort of looked. I did update this PDF right here with the values that you should use for the second Jupyter notebook. If you have any questions about that, please let me know. But that notebook is already up here. And then the other thing that I wanted to point out was, let's see, I posted a link to the lecture notes right there for chapter 9. And as we finish every chapter going forward, I'll post my own notes. But again, this doesn't mean that um, you shouldn't take your own. In fact, it's probably good if you do. And then on the resources somewhere, I think under important documents, I posted not important documents. Um, huh. So okay, looks like I didn't post it. But what I wanted to show you, so let me see if I can pull it up really quickly. Documents. Sorry. I thought I posted it, but I'm gonna post it later. So it would be this document here that you would get pretty much for every exam. It's an equations and constants sheet. So if you're ever wondering what you need to memorize for exams, really the answer is nothing that involves equations or numbers, because I'll give those to you. So, you have a whole list of physical constants, units, and like convert different unit conversions, SI stuff, the Greek alphabet, because I mentioned that is pretty important. At least I'll bet you use most of these symbols by the time you're done. Logarithms, exponentials, X series expansions, differentiations, integration stuff. And you will get all of this for every exam. A lot of this is taken from either this book, sort of towards the end, there's an appendix for integrals and stuff, or from the other PChem book that I've been using. It's called by Atkins and DePaula. And then I will also give you these sort of useful integrations from every chapter. So from chapter 9, you'll get sort of these equations. For chapter 10, you'll get these equations. And so this is what you'll get for the first exam. And as we go into the second exam, I'll add in more and more chapter stuff. Does that make sense? So I thought I posted it already on ACE, but I did not. So I'll put it under resources and maybe important documents. I'll put it under important documents. But yeah, I'll make a print out of that, and you'll each have a copy of that for the exam. Sounds good? All right. So let's get started. If you have questions again, please just don't hesitate to ask. So the last time we were here, we finished up chapter 9, where we went over all of classical mechanics, which is mostly founded on Newton's laws of motion. So we went over Newton's equations of motion and some variations of that. But then we started talking about some phenomenon in physics and science where we could not explain things, and we went over 4 types of those phenomenon. But then we also talked about how we could sort of explain some of those. For example, we looked at photons and black body radiation. Whoops, black body radiation, and we could explain black body radiation, at least Planck did, by assuming that the energy of a photon is quantized, right? Or rather, that energy of light is quantized, and he called those little quantized particles of light photons. Einstein also studied the photoelectric effect and came to the same conclusion. right? That light is quantized. And then another sort of confusing phenomenon we looked at was the structure. So structure and spectrum of hydrogen, right? And while we couldn't explain it, Bohr came up with his model, right? That sort of explained the spectrum pretty well. And we went over the Bohr model last Thursday. Now, I should remind you that in the Bohr model, right, it's a weird model of like a solar system, like atom, and the atoms are, and the electrons are fixed in their orbits, and they can't move except when they absorb and emit an electron. And the whole thing seems weird. But at this point, so this is the early 1900s, at this point, people were like, well, something is clearly wrong. We need a better theory. And I'm going to basically tell you what that better theory was, or you probably guess it by now. It's quantum mechanics. But I'm going to show you how it was developed slowly from just sort of the thought process of it all the way through to the established theory that we know. Now, at this point in history, right, people are thinking, hey, we need a new theory, and this theory should describe particles like waves, right? Because everything seems to be both wave-like and particle-like, especially light, right? So people were starting to wonder that maybe particles, and by particles here, I mean all the subatomic particles, protons, neutrons, and electrons, should behave wave-like. Now, in this course and most of chemistry, chemists don't really care about the protons and neutrons. I know this sounds silly. Really, we only care about the electrons. We leave the protons and neutron stuff for physicists. So really, most of what we're going to talk about when we talk about quantum mechanics is how electrons move. And so we need a way to describe electrons moving as waves, right? And so the way we came up to do that, the way we go about doing that is by using something we call the wave function, right? Now, I want to point out that in your textbook, they spell wave function as one word. That's wrong. Wave function is two words. All right, so let's just look at some of the objectives for this bit here. We're just going to look at how understand the quantum mechanical wave function and its constraints. All right, so we need to describe electrons as waves, and the way we can go about doing that is by using wave functions. Now, what is a wave function? A function in math, right, is really any sort of combination of variables and constants that give you, let's say, a plot on a graph, right? So if you think about the simplest wave function, the simplest function that can describe a wave, right, you might think of a sine wave. So let's say that's x, that's y. A sine wave would be something like y is equal to sine x, right? So sine x, so sine of 0 is 0, sine of 90 degrees or pi over 2 is 1. So let's say that's 1, right? Sine of 180 degrees is 0 again. And it continues like that. That's a sine wave. And you're all sort of familiar with sine waves. A wave function is really no different. A wave function is just any function, or any wave-like function that can describe what we're looking at. And in particular, if you look at sine waves, you can build wave functions from sine waves, right? And the way we go about doing that, we might be something like this, where we sort of take the sine wave and just multiply it by things to change it in various ways. So in this equation here, A, B, C, and D, for example, will all change this sine wave in different ways. It'll stretch it or shrink it, or stretch it horizontally or vertically, or shift it, that sort of thing. So we need functions to describe electron motions as waves, and sine waves are an example of wave functions. in your next Jupyter notebook, you're gonna look at a simple sine wave like these and try to figure out what all these A, B, C, and D things would do to the wave, like I mentioned. Sounds good? All right. All right, so we're going to describe particles as waves, but we need some rules, right? We can't just use any old sine wave and be like, all right, we're going to use this wave for an electron. No, we need some rules. Not any old waves will do. So we need to sort of set some ground rules, and I'm not going to sort of show you all the different things that people tried when they were trying to set up rules and stuff when they were just developing quantum mechanics, because one, I don't know all the things that they tried and failed. But I'm going to show you the one that somebody tried and worked, and it's what we use today. And so hopefully by doing this, I give you sort of an understanding of how people can sort of develop a comprehensive theory. So let's start out with setting up some ground rules. So let's set up ground rules. And we'll call these ground rules postulates, because really that's what a postulate is. And what these are going to be statements we assume to be true. And not really true because we wanted to, just based, we're going to assume that they're true based off of observations, right? But really, we're not going to go into why they're true. Remember last time we met, I talked about how physicists don't really answer questions of why, they just answer questions of how. So it's to set up these ground rules for how this whole new theory is going to work. We're going to set up these postulates. We're going to just assume that these postulates are true and then go ahead and build our theory around these postulates. Where I'm not going to prove that these postulates are true, because really we can't prove whether or not they're true, right? That's answering the question of why. Like I said, that's probably more for philosophy and religion, a question for philosophy or religion. But we're just going to set up these postulates and, let the chips fall where they lay. So our first sort of postulate, quantum mechanical postulate number one, let's use a nicer pen. For our first postulate, we're going to say that the behavior of a quantum mechanical system, for example, electrons in our case, can be described by a mathematical function, a mathematical wave function. And since we want to keep things consistent, we're always going to use the same symbol for this wave function. We're going to use this symbol. And this symbol is psi, capital psi, right? It looks kind of like a trident with a little bar on top and bottom just to separate it from the capital one. But that is our first postulate, is the behavior of any system can be described by this wave function psi, and then all information about the system is contained in this wave function. That's our first assumption. Whether or not this is true, we don't know, and really we don't care. We're just going to assume that this is true and then build a theory off of it. For those of you wondering, this is capital psi, right? Greek symbol psi, and lowercase psi just looks like that. Just learn to write the two in ways that you can differentiate them. But the capital psi is what we're always going to use for our wave function. So we're going to write this a lot this semester. All right. So that's our first postulate. So whatever system we're working with will be described by this psi. Does that make sense to everybody? Right? Psi could be a psi function like we did, sine function like we did up here. It could be any function that we want. Well, really it can't be any function that we want, right? Like kind of, I don't know if it can be a function like that. That's a function probably, but it can't just be any function. So we have to put more restraints on it. And so let's talk about that. So let's talk about some of the constraints on psi. What can psi be and what can psi not be, right? So not any wave function works. And some constraints would be, all right, let's explore them one by one. The first one will be psi must be single valued. What does that mean, single valued? Well, if you have a function, right, kind of like that. Let's use a different color, like that. Single valued means for every one value of x, there's only one value of y. That's what single valued means. If you had a different function, let's say something like this, that's not true, right? For this value of x, there's one value of y here, a value of y there, and a value of y there, not single valued. So single value just means there's a one-to-one sort of relationship. I guess we can write that. One-to-one between x and y, well, or x and psi. Does that make sense? So that's our first sort of constraint. Psi must be single valued. All right, let's look at another one. Psi must be continuous. I think we all sort of have an idea of what continuous means. Continuous just means there are no breaks. There are no breaks in psi. So for example, if you were plotting psi, right, and there's like a piece there, and then there's a break and a piece there, and there's a break and a piece there, right? That wouldn't fly because psi must be continuous. It must be one continuous sort of function. Does that make sense? All right. So let's look at another one. Psi must be differentiable, which really just means that psi must have a gradient. Right? So the gradient must not like be infinity. So sometimes you might see a graph like this. Let's say this is the wave function, and then it goes like that, and then it goes like that again. This is wrong for a number of reasons. One, this here means that it's not single valued, right? But also it also, there we go, not single valued. But it also means that it's doesn't have a gradient, right? Because if you think about what the gradient is for this part here, it's kind of infinity, right? The rise is something, but the run is 0. So the gradient is infinity. Doesn't have a gradient. And it actually is not continuous. So there's many things wrong with something like this one, right? Does that make sense? But yeah, it must have a gradient. And then lastly, the last constraint that we're going to put on this is psi must be bounded. And that simply means psi must not go to infinity. Right? So any wave function that you see that goes up to infinity can't work. All right, so we're setting up some ground rules for this new theory that we're going to develop. We talked about how everything in this new theory is going to depend on this wave function psi, and now we're gonna put some constraints on psi, and these are the constraints. Does that make sense? So what I want you to take away from this are these 4 rules, and I want you to sort of be able to identify just by looking at a graph of some function whether that will be a good wave function or not. So there's some examples in your book, and we're going to go over some examples, I think from exercise 10.1 at the end of chapter, also in the Jupyter notebook. But just sort of be able to recognize when a wave function is okay and when one is not okay. Sounds good? Yep. Yes, no? Okay, great. All right, any questions for me about this wave function business, Sai?
Isn't there a fifth?
Is there a fifth? What is the fifth?
Isn't there a fifth constraint?
Yeah.
We talked about.
Is there? I don't know. Let me look at your textbook. I'm going off of memory here. What is the fifth constraint that you remember?
I don't quite remember the exact wording. It was.
All right, I'm going to look this up. Let's see.
We talked about it in inorganic, if anyone who took inorganic remembers.
Your textbook only has 3 constraints. So I give you an extra one. And really, like I said, these 2 constraints, I'm not sure which 2 they put together, but these 2 constraints can be thought of as the same thing. Because if you're not continuous, then your gradient is crazy. I'm not sure what's the 5th constraint that you looked at in inorganic, but if you do find out what that is, let me know. Some people say that psi must be twice differentiable. So there's like the first gradient and the second gradient. I don't know if that's the 5th grade constraint. That's not necessarily true, or it doesn't have to be true. But for now, just think of these as an easy way to spot when a wave function is good or not. Right? All right. So we want to describe an electron using a wave. We're going to do that by using some random function we call a wave function. And so that's the first postulate. And then we just went over some of the restrictions to this wave function. Everybody with me so far? All right. But then how are we going to use a wave function to describe things, right? Like, what is the math behind there? How are we going to do this? And so this brings us to our next sort of subsection called observables and operators. Now, so far, everything that we've done, for example, in the last chapter, talks about how to use Newtonian mechanics. And we used it in different ways, and a lot of it depends on calculus. Now that we're looking into wave mechanics or quantum mechanics, the math is probably very unfamiliar to you. Though, if for anybody who studied these things, for example, if you did like a whole undergraduate physics course, these things would be all very familiar. So observables and operators just sort of helps to teach you some of those math that you might not be familiar with. So some of the objectives here would be to describe an operator, to solve eigenvalue equations, and we'll talk about what those are, and to apply the position and momentum quantum mechanical operators. All right. So we have a wave function psi. And according to the first postulate, I mentioned that everything that you want to know is in that wave function, right? But then you might be asking, how do we get that useful information out of the wave function? Or at least, if you weren't asking it, you might be thinking it now that I mentioned it. So how do we get useful info out of psi? Because if everything is in psi, how do we get all the things that we want out of it? And that will bring us to our second postulate that we're just gonna, again, assume without sort of proof. And according to this postulate, we're just gonna say that every physical observable meaning everything that you can actually observe, and let's call an observable, let's call it O for a symbol, right? Corresponds to a Hermitian, and I'll come back to what that means, operator, and we'll give it the symbol O hat. Right? So anytime you see this little thing above it, we'll call that a hat. And it means that we're looking at an operator. Right? So this is our postulate, and this is our second postulate. But what does this mean? What is
So question, are like X, Y, and Z then operators of position? Is that correct? Okay.
And again, this is X, Y, and Z are variables, but they're also operators. We'll get to that in a second. But yes, essentially. All right. So let's say you have a wave function and you want to know how fast the particle is going. There's an operator for that. You want to know what's the energy of the particle. There's an operator for that. You want to know what's the, I don't know, anything that you can think of for the particle, there's a corresponding operator. So if I mentioned you want to know the velocity, there's a corresponding velocity operator. You want to know the position X, there's a corresponding position operator. You want to know the energy, there's a corresponding energy operator, right? That's how operators work. Now, let's just look at operators in a more sort of general way. Operators basically take input, input number and their functions, computer's starting to slow down already, and returns an output. Could be same, could be different. An output number or function. Right? That's all an operator means. So I think your textbook has some very simple example. Let's look at the operation 1 plus 2 equals 3. Right? This here, right there, this here is the operator. And really it's the addition operator. So, I mean, we know that, right? These here would be the inputs. And this is the output. That's a very simple operator. It takes two numbers, in this case. I spelled input really wrong there. It takes two numbers, and then it spits out another number as output. Right? That's an operator. Now they could be more complex. For example, instead of writing it as a plus symbol, and we only write as a plus symbol because we use this so often that we have a special symbol for it. But not all operators have a nice way to write it. So for example, we could call this symbol the addition operator, right? A for addition, and with the little hat on it to say that it's an operator. And we could say that this operator takes two numbers, let's say 1 and 2, and it spits out an output 3. So in theory, we could take this expression over here and rewrite it like that to be more general. Everybody still with me? So here, this is the operator, right? These are the inputs, and this is the output. It's the same way to write the equation above, just in a more general way. So here is something, though, that I want us to focus on. In quantum mechanics, we only use unary operators. Right? What that means is unary here means operators with only one input. Please let me know if I'm going too fast, because I think all of these would be new math and new concepts at this point. So if you want me to slow down, please let me know. So the plus symbol, yes.
So like when, like going, for example, with our Jupyter Notebook thing where we did that ZT function. So Z would be the operator there, and then time would be the input, and you would only ever have, so you wouldn't ever have like multivariable systems with quantum mechanics.
You can stack operators on top of each other.
Oh, okay.
You can stack operators, so you can have multivariable inputs. But so yeah, and we'll see how that works in a second. So, but in quantum mechanics, we only do unary operators. So addition here, looks like a binary operator, right? It takes two inputs and spits out one input. But really, addition operator can have any number of inputs. You can add 1, 2, 3, 4 all together, right? And this will give you 10, right? So addition can have many different inputs. But in quantum mechanics, we can only have one input. So, really, we can do away with it will only take one input. So let's say you're adding 2. I mean, it's just addition as a unary operator makes no sense. But because there's only one input, we can do away with the parentheses like that, and we can just be the addition of 2 is 2, something like that. Does that make sense? I just want to show you sort of how you write these things down. So here we'll have the operator, the input, and then the output. All right. So we're only ever going to use unary operator, so we don't need to put parentheses. You assume that the input follows directly from the operator, right? So you write operator first, then input. All right. Again, you could also use functions as input. So functions as input, right? So let's say you have some function of x, I don't know, 2x plus 3, right? And let's say you have some operator b that you want to apply on the function. This is how you would write it. The operator, then the input. The input is a function. Does that make sense? So operator and input function. Everybody with me so far? So all of this so far is just sort of the getting you familiar with the language of math that we're going to be using. So anything can be an operator. I give you an example of
Could you
plus
scroll up
symbols.
some?
Sorry?
Could you scroll up some?
Oh, sorry.
Thank you.
Quick question. How is
Yes.
an operator different from a function?
Okay, let's talk about that now then. So functions can be operators. Yeah. But how are they different from a function? Well, there's some things that are not functions by themselves, but can be operators. For example, plus, a plus sign, it's not a function, right? But it's an operator. And it can't serve as a function. Here's another example. Are you still writing? All right,
You're good.
let's use a more complex operator, right? Complex operator. And let's use the operator ddx, the differential with respect to x. Or we can give this the symbol d for differential with a little hat on it. Again, these operators, I'm just giving them random letters because I want to, right? D seems like a good letter for a differential function, a differential operator. So let's use ddx, right? So let's say we have some function f of x is equal to, I don't know, e to the 2x, something that we can differentiate easily, right? If you want the differential of this function, ddx of f of x, you can rewrite this instead as just df. Do we see how that works? And if you're going to solve this, it's just going to be d dx of e to the 2x, which is just equal to 2e to the 2x. For those of you not familiar with differential. Is everybody comfortable with doing differentials like that? Yep. Yeah? Okay, good. If you're not, just let me know. We can go over some calculus too. But let's look at this a little bit more detail. So we have d of f, right? The operator on f is equal to 2e to the 2x, right? And we know that f is equal to e to the 2x. For this example that I just gave you, which means that, so d here is the operator, f is the function. But look at this. Here's e to the 2x. It's the same function. And here, this is just a number. Right? This is actually a very special case of operator function combination. So when you have an operator function combination that returns the same function times a constant. Constant here just means a number. We call these equations eigenvalue equations. So in this example here, right, we could have written this as the differential operator on some function returns a constant. In this case, that constant was 2 times the same function. Do we see that? And I brought this up because we're not going to be talking about general functions anymore, or general operator functions combinations. We're only going to talk about situations where this is what happens, because that's what is important. And in case you're wondering, eigenvalue here is German. I think it's German. German for own or specific. Is this all making sense? So we're looking at operators. Yes, fine. Operators act on functions, fine. And it's a unary operator, so there's only one function that it acts on. And it returns something when you apply it. But if it returns the same function times some constant, that's an eigenvalue equation, right? And so in those cases, that's your operator. And we call these specific kinds of function that this happens to, because it doesn't happen to every function, we call these eigen functions, right? Remember, eigen means same, so it returns the same function. And the number that it returns, we call this the eigenvalue. And that's where the equation gets its name from, eigenvalue equations. Everybody with me? All right. So if you want to generalize this, basically you have an operator, a function is equal to some constant times the same function, right? And I think K, this is how your textbook has it. So let's do that. Operator, the F's are the eigen function, and K here is the eigen value, which is just a constant. I know I'm throwing a lot of things at new stuff at you right now, so please ask questions. All right. All right, hearing none. The other thing that I introduced in the second postulate, remember, was that operators that correspond to observables must be Hermitian, right? And you're probably wondering what this Hermitian thing is. And it sounds a lot like Hamiltonian, but it's a very different word named for a very different mathematician. But they all have similar names. It's boring. But let's talk about Hermitian stuff, because we talked about unary operators has one input. We talked about eigenfunctions and eigenvalue equations, which have the input is returned as the output times a constant. So let's look at this last one, Hermitian operator. I said that in quantum mechanics, and we just lost somebody. In quantum mechanics, an observable is related to an operator, but the operator must be Hermitian. All this means is they have real, not complex, eigenvalues. Right? So the number that it returns, the constant that it returns is going to be real, not imaginary or complex. And if you think about it for a little bit, this sort of makes sense, right? Let's say you want to find, let's say you want to find a velocity of a particle. You have a velocity operator, right? The number that you get back can't be complex because velocity is a real thing. You don't measure velocity and be like, oh, the velocity of the car is 20 miles plus I times 40 miles, right? Like it's not a complex number, it's a real number, right? Remember, complex numbers look like something like, I don't know, 20 plus I, or how do I, 20 plus 5i, right? That's a complex number. But if you were measuring the velocity, there's no such thing as a complex velocity. It'll only have to be real. So whatever operator you use to get the velocity must only spit out a real number, not a complex number. That's what Hermitian means. It will spit out a real number, not a complex number. Make sense? We just have to define these things because, you know, there's going to be some mathematician out there be like, well, why don't you use this operator? And be like, no, we need a real answer, not an imaginary answer. Okay, any questions on that? So we have a wave function psi, right? We have operators that correspond to some real observable, and we have eigenvalue systems where if we apply some operator on some function, let's call it the wave function, why not, return some constant times the same wave function. If this does not happen, then it's not an eigenvalue equation. Make sense? All right, let's do some for practice. All right, so which of the following operator function combinations yield eigenvalue equations? Right, and I'm gonna do a few of them. So this is the first operator, and this is the first function. This is the second operator, it's the second differential, and this is the second function. And this is the third operator. Let's do the second differential again. And this is the second function. So I want you to attempt these, apply the operator to the wave function, and see if you get back the same wave function. And if you do, then it means that they were eigenvalue equations. I'll give you a few minutes to do that. If you're not sure, please like raise your hand and I can do the first one as an example. But I do want you to try it on your own first. Is there anyone who's not sure how to proceed? No? Okay. In case you're wondering what differentials and second differentials of trig functions are, right? I don't expect you to memorize these. This is why I'm going to give you that equation sheet in your exam. And I guess once I have it posted up there, it might be good to just print it out so that you have it for a quick reference for those different integrals and differentials. But I'll do the first one. So remember, to set up an eigenvalue equation, you need operator and function. So the operator is d dx. The function is sine 2x. The differential of sine is cosine, right? D dx of sine x is just cosine x, right? Everybody remember that? So d dx of sine 2x is just going to be 2 times cosine x. Whoops, cosine 2x, sorry. Does that make sense? All right, now let's examine this to see whether it's an eigenvalue equation. And right away, you're probably thinking, no, it's not. Because here's the operator, here's the function, right? Here's a number, yeah, okay, that could be the eigenvalue, but this is not the same function. Right? Does that make sense? So as soon as you see that it's not the same function, this means that it's not an eigenvalue equation. Let's try the second one, right? Our operator is d squared dx squared, so it's the second differential. Our function is the same function, sine 2x. We know that the first differential is 2 times cosine 2x. So we need one more differential of that. And the differential of cosine is minus sine, right? So this becomes minus 4 sine 2x. And now if we examine this, here's the operator, here's the function, here's a number, -4, and here is the same function. Same function, which means this is an eigenvalue equation. If you're not comfortable with this sort of math, please speak now. I can go over this in a little bit more detail for the differential, but if you don't speak up, I don't know. I'm assuming, right now, I'm assuming we're comfortable with this level of calculus. Yes? Okay. If not, please let me know, right? Don't be ashamed to speak up. Sometimes when you do something a semester ago, 2 semesters ago, or whatever, by the time the semester is over, you already forget everything that's in there. So who knows how long ago you took this sort of calculus. But there it is. The second one is an eigenvalue equation. And I'll leave the third one for you to figure out. But try to do the second differential of that number and see if you get back the same number or not. Actually, you know what? I'll do it because I like doing math. All right. So here's our operator. Here's our function. All right. So first, let's take the first differential. Now, when you have a complex problem like this that you wanna do the you want to find the differential of, you might want to use the chain rule, right? Do people remember chain rule in differentiation? So you let some other variable, I don't know, let's call it u, is equal to the number 2x squared, right? So du dx will be the differential of u with respect to x would be 4x. Does that make sense? All right. So the function, the original function, becomes e to the u, right? So let's say we'll call this function f. I don't know. So df du is also e to the u. And so df dx is equal to df du times du dx. So we get e to the u times du dx was 4x, right? So this whole thing, so df dx becomes e to the 2x squared times 4x. I did all that math and I lost somebody, or we gained somebody. I'm not sure. Does that make sense? All right. Now we want to do this differential one more time, right? It's the same business. Now we need to use chain rule and we also need to use product rule, right? So product rule, because this has two parts, so we're going to separate them. So let's say this function is now, the new function is 4x times e to the 2x squared. We'll call this part of the function, I don't know, we'll call it a. And we'll call this part of the function b, right? If you remember your chain rule, df dx is equal to a times db dx plus b times dA dx. Remember that chain rule? There's a lot of calculus in this course, unfortunately. So I wanted you to just get familiar with these sorts of chain rules and stuff. So let's do each of these differentials by themselves, right? And then we'll put it all together. So b, we just said, was e to the 2x squared. So db dx, we already found that out, right? Right? This is db dx. It's just 4x e to the 2x squared. All right, let's look at the other one. Let's look at this one. We said that a was 4x, so dA dx was just 4. So everybody still with me? So let's put this all together. df dx is equal to a, right, which is just 4x, times db dx, which is 4x times e to the 2x squared, plus b, which is e to the 2x squared, times dA dx, which we said was 4. Everybody still with me? I see some faces. All right, all right. And then we can just simplify this at this point. E to the 2x squared can be pulled out. And then you have 4x times 4x is 16x squared plus 4. Yeah? So this is df dx, which is actually the second differential of the function that we started with. So you could do all of that, or you could do this. I'm going to teach you how to do this on, what's the thing called? The Jupyter notebooks. I'm going to teach you how to do differentials on the Jupyter notebooks. And you can literally do all of this that we just did. And in fact, you guys did some of this in the first one. You can do pretty much something as complex as all of this in just like 3 or 4 lines of code. Not that I don't want you to do math by hand, but whenever you do math by hand, it's nice to just have a way to check the answer really quickly. Here's another way, for those of you wondering, here's another way that you can actually do this, this fast. So if you should be seeing my browser, right? So if I go to Wolfram Alpha, right, I could do d squared dx squared of e to the 2x squared, enter, and there's our function. Right, that's it. Literally took me 10 seconds to verify that differential.
What was
Does
that
that
called?
make sense? Yeah, sorry.
What was that called?
Wolfram Alpha. Let me see if I can type. I'll type it in chat.
Thanks.
There. I think it's free. Yeah. Well, most of the features are free, so you can use that as well. and play around with it. You see, the reason why I'm showing you all of these tools is that this is not a math class. There's a lot of math in it, but this is not a math class. This is also why I give you that entire equation sheet. You're going to get that entire equation sheet for exams. Because again, I'm not testing you. I don't want you to learn math. You need to know math to do the physics, but this is not a math class. So whenever you're doing anything outside of an exam, because you won't get this in the exam, you can verify your answers using the Jupyter notebooks. You can verify your answer using Wolfram Alpha. If you're in an exam, you get the equation sheet. But if you need help with the math, please let me know, because you know, advanced calculus is sort of a prerequisite for the course, and there's going to be a lot of it in here. But I don't want the math to be sort of the thing holding you back. So let me know if you're not comfortable with the math. Sounds good? All right, so any questions on operators or eigenvalues so far?
Is the one,
Yeah,
sorry, go ahead.
Is C an eigenvalue equation? Because
Is C,
like,
oh, right, sorry. Good, we didn't answer that question. So this was our operator. This was our function. And you might look over here and be like, well, there's the same function. But no, this is not a constant. Right? There's x in there. Right? X is not a constant. X is a variable. So this is not an eigenvalue equation.
all right, thank you.
You're welcome. Yeah, thanks for asking that. I forgot that that's what we were aiming for with this question. And I went off on the math part of it. But yeah, that's not an eigenvalue equation.
So when we were talking before about when we were setting our postulates that the equation has to be differentiable, does that mean the first derivative of whatever our equation is has to be an eigenvalue?
No.
No. Okay.
No. It just means that the derivative must exist.
Okay.
They're things that you can't find the derivative of. But any decent function should have a derivative that you want to use for a wave function. Because the derivative alone by itself is not an operator that we use in quantum mechanics. It's used in conjunction with other things to make operators that are useful. In fact, let's talk about some of those, right? Sorry, you had another question?
No, that was it.
But yeah,
Thank
no,
you.
that's not what I meant by it must be differentiable. The differentiation of it should not be an eigenvalue equation necessarily. It could be, doesn't have to be. All right, so we know that we must have wave functions, and it's good to always remind yourself of these different postulates. So the postulate number one means that we must have a wave function, and we talked about how those wave functions are sort of what they should be and what they can't be. We talked about the second postulate, which means that if we want some observable, we call it O, it must relate back to some operator, O hat, right? And the operator must be Hermitian, which means it returns a real number and all that good stuff. Well, okay, but that doesn't, like, it doesn't now help us develop a theory. Like, we still need more steps here, right, to come up with a good solid theory. So let's come up with another postulate. And remember, all of these postulates are just things that people assume. If you want to think about how to develop this, you can imagine some scientist just sitting in his basement or wherever he's sitting, I don't know, in the library, trying to come up with ways to make the theory work. And these postulates are just assumptions that they have to make the theory work. And then after you have the theory, then you can figure out, oh, is this a good theory or is this a bad theory? Kind of like what we did for the Bohr model last Thursday. He just made a bunch of assumptions and it worked, but none of the assumptions that he made sort of really made sense. So it wasn't a good theory and it only worked for hydrogen. These postulates are more grounded in sort of mathematics and reality and observation. And so we don't have an explanation for them, but they seem to make more sense. So let's look at the third postulate. And so we talked about how observables relate to measurements, and these measurements come from operators. And so in the third postulate is going to be the only observable. So the only possible observable observable value, let's say, that you can obtain in any single measurement are the eigenvalues of the eigenvalue equation from the corresponding operator and wave function. So I'm sure many of you probably guessed this is where we were going when we started talking about eigenfunctions as special types of functions with operators. But let's say I'm going to make some, many of you are still writing. I'll pause for a second. So let's say you wanted, I don't know, the kinetic energy. So that's a kinetic energy operator on the wave function, right? We set up an eigenvalue equation, and let's say this is the kinetic. There's too many k's in this world. Let's say T is a kinetic energy, right? The only kinetic energy you can get from any measurement is this eigenvalue, right? If it's not an eigenfunction setup, then you can't get that eigenvalue from the measurement. Does that make sense? We talked about how this wave function contains all of the information, but that means that you're limited to what answers you can get. You can only get the answers when you sort of plug in the operator on the wave function. Yeah? Does that make sense?
Again, please?
Was there a question, sorry?
Yeah. Can you hear me?
Oh, wait, sorry. Hang on. Let me raise my volume. You're very quiet.
Can you hear me now?
Slightly better.
Hello?
Yep. Okay, it's very loud. That's good.
Oh, hey, so I was wondering if you can say that again, please.
Okay, so let's say you have a wave function. And we said, according to the first postulate, that wave function contains all information about whatever we're looking at. Let's say the electron. And let's say that we want to pull out one of those information. We said that the observable is related to the observable operator. Any observable is related to the operator. So let's say we pull it out and we get that observable. Well, the third postulate says the only observable you can get is the one that comes out. I know there is a slight sort of nuance between the second and the third postulate. This second postulate just says observables are related to operators. The third, right, so it just says that. The third postulate says that the only observable you can get are the ones that you can pull out in eigenvalue equations. Again, subtle, but all right, let me give you an example of where it doesn't work. Let's say you have an observable operator. I don't know. Let's say it's kinetic energy again, right? You apply this to the wave function, right? You could set up a situation where it's not an eigenvalue equation where you get some 5x plus 3 or whatever times the wave function, which means this is not an eigenvalue equation, which means that this here is not the kinetic energy.
So is it just saying your observable has to be a constant, essentially?
Essentially, somebody could rewrite this, right, to be a this could be a new function and the constant is 1, right? So that's why they must relate to eigenvalue equations, because then we won't know sort of where they come from. Yes, the observable must be a constant, but they also must relate to eigenvalue equations. I know it's hard to give you a counterexample when the straightforward case is just this. Everything else, anything else doesn't work. And I know you're all sort of scratching your head and probably asking, why is that the case? Short answer is we don't know. It's a postulate, right? It's just something we're going to assume to be true without proving it. I'm not going to prove it. I don't know if anybody knows how to prove it. We're just going to assume that this is going to be the case. Anytime we want an observation of something, we need to have an eigenvalue equation. If we don't have an eigenvalue equation, either we can't do that observation or the wave function is wrong, right? Does that make sense? And this is going to relate a little bit in the future when we talk about like what things you can observe and what things you can't observe. But so we've been talking about observations and observables and operators that make those observables. But what are those operators? Like I talked about the kinetic energy operator, but what does that look like? What else? Yeah, so really there's only 2 operators that are of major importance, right? The first one is the position operator. And I think somebody, maybe Aaron, alluded to this earlier. So we can write the position operator like that, right? The x position as an operator, the y position as an operator. And when you want to know what this actually looks like in mathematics, it's just x multiplied by whatever comes after it, right? So let's say, for example, your function is, I don't know, I'm going to make something up, 3y plus z. Let's not use y and z. Those can be 3a plus b, something like that, right? So if you apply the x position operator on this function, it's just going to be x multiplied by whatever the function is. Does that make sense? And this is position in x space. You could imagine the same one for y space and z space, right? It's just going to be y dot or z dot.
Just to clarify, x is a constant, right?
Variable.
Okay.
X is a variable. It changes depending on where you are in the graph. Constants usually refer to things that don't change. So pi, the number of pi is always the same no matter what you do. So we call that a constant. Or like numbers. The number 1 is the same no matter what you do. So that's a constant. But things like x is a variable because it can change depending on, let's say you're looking at a graph, x here is 0, but x here can be 5, so it changes. And whenever you see x, y, and z, you assume them to be variables. And when we say that, we mean that you can actually do differentiation with respect to x or y or z. You can't do differentiation with respect to a constant, right? Like you can't do df d3. That doesn't make sense. Like your differentiation thing, the function with respect to a constant, or d pi, pi is a constant. Doesn't work. whenever you see numbers like A, B, and C, they can be constants or they can be variable depending on how the problem is set up, right? In this example, A and B are variables. So if I wanted to like specify that A and B are variables, I should have written f as a function of A and B, right? Does that make sense? Again, this is just all the language of math that I want you to be comfortable with. In a lot of cases, A and B could be constants, and then I will tell you A is a constant or B is a constant. That means that you can't differentiate it. You treat it just the same way as you would any other number. Everybody with me on that? Again, please ask your questions because I know this is all very new math for the most part. The calculus might be familiar, but the way we use it is very new. All right, so I said there's two operators. So here's the position operator. And the second one that's important is the momentum. Or really, it's a linear momentum. There's different kinds of momentum operator. And so remember P we use for momentum from Hamilton's equations, right? I told you it's going to come back. So we can write a momentum operator with P hat. And since momentum can be in X, Y, and Z space, I'll put a little X there to show you that it's an X space. And this is what, this one looks weird, but this is actually the operator. Negative I H bar d dx, or partial of d with respect to x. The partial of the differential with respect to x. So this is momentum in x space. I here is a complex number, right? I is a square root of -1, right? We were familiar with complex numbers, right? Yeah. I is the square root of -1. H bar is just h, which is Planck's constant, divided by 2 pi. And d dx here, this here is del. It's not a Greek symbol, but it looks like one, doesn't it? It's del, and it means partial derivative. And really, we only say partial derivative because we don't know what function comes after. Right? Because this is the operator, and then you add the function afterwards when you're doing the operation. So these two are the two most important quantum mechanical operators, position and momentum. Every single other operator you can derive from these two. But I know we went over a lot of new things here. I'm just going to spend the last couple of minutes. Well, let me pause for a second and ask if we have questions. No. So we went over a lot of new things. I'm going to make a space over here. We decided that we need waves to describe how things move, right? And so we need to develop a whole new theory based around waves. And to make this new theory, we needed some postulates. Yes.
So going back to the with momentum in relation to the Hermitian operators, so you can have a operator that includes an imaginary number so long as the eigenvalue will not include an imaginary number.
Right. The eigenvalue must be real. It never said anything about the operator.
Okay.
In this case, the operator has a complex number in it. So you might be thinking, oh snap, what's going on over there? And so that means then that we have to choose our function carefully, right? So that when we get the eigenvalue, it's real. That's all that means. But yeah, the operator can be complex. The eigenvalue must be real.
Okay, that makes sense. Thank you.
Welcome. So we needed to come up with some postulates and some rules. The first one, again, talks about the wave function. And we talked about how the wave function must be single valued, only one value of psi for every value of x, must be continuous, meaning no breaks, must be differentiable, meaning it must have a gradient, and must be bounded, meaning it mustn't blow up to infinity. Then we talked about the second postulate, which means that which just tells us that any operator must come, any observable must come from an operator. That operator must be Hermitian, meaning that it must return a real eigenvalue or a real value. And then the third postulate was these operators must come from eigenvalue equations. And the only observable that you can get are those from the eigenvalue equations. And then finally, we ended it by talking about two operators that are very important. The first is the position operator, which is just x multiplied by whatever comes after it. And the momentum operator, which is just negative I h bar, partial derivative of x. I would encourage you all to sort of, oh, we're over time, but I would encourage you all to go over the examples in the textbook. As always, the examples that I show you in class are different from the ones in the textbook. So you have like a double whammy of like examples to look at. So look over the ones in the textbook and just let me know if there's anything that still seems confusing. We can go over those because again, this is all new stuff. It's okay if it seems weird. These postulates, as I mentioned, they're just things that we assume to be true without proving any of them. Any questions or any before we break off for today? Nope. So yeah, I'll just let that digest in your brain matter, and I'll see you all on Thursday. Remember, the second Jupyter notebook is up. I still haven't gotten a couple from the first submissions for the first Jupyter notebook, so please remember to submit those. Otherwise, see you all bright and early Thursday morning.